Today, we are going to present our work, Distilling Long-Tail Datasets, which has been accepted to CVPR 2025. This is a joint project by Zhenghao Zhao, Haoxuan Wang, Yuzhang Shang, Wang, and Yan. Dataset distillation aims to synthesize a small dataset, such that a model trained on it can achieve comparable performance to one trained on the original large dataset. A long-tail dataset refers to a dataset where the number of samples per class is highly imbalanced, which is frequent in the real-world scenarios. However, we found that the existing dataset distillation methods perform poorly on long-tail datasets, as shown in this figure. When the imbalance factor increases, meaning the dataset becomes more imbalanced, the performance of dataset distillation methods even drops below that of the random selection. There are two key reasons behind this: inconsistent weight distribution between student and expert network, and suboptimal performance for expert models on long-tail datasets. Let's first take a look at weight distribution issue. Here is a weight norm trajectory of an expert network they're retraining. For head classes, the weight norm grows quickly, while for tail classes, it grows slowly. This imbalance leads to poor performance on the tail classes. When applying traditional dataset distillation directly, the student model shows a similar imbalance. In contrast, the student model trained on our method exhibits a more imbalanced weight growth, leading to better performance on tail classes and overall improvement. Now for the poor expert inference capability issue. The main problem lies in the soft label initialization. As shown in this figure, for head classes, all methods gave high confidence, but for tail classes, traditional dataset distillation methods yield much lower confidence. To address these two challenges, we propose distribution agnostic matching and expert decoupling. Let's take trajectory matching as an example. In traditional dataset distillation, the expert model MD is trained on the real dataset D, and the student model MS is trained on the synthetic dataset S. The goal is to match their training trajectories. However, due to the mismatch in weight distribution, directly matching their trajectories causes information loss on tail classes. Our solution, distribution agnostic matching, allows the student to mimic the training behavior of parameters trained on the original dataset to mitigate the information loss on tail classes. Specifically, we redefine the trajectory matching loss by modifying the cross-entropy loss into a sample-aware probability, enabling better tail class learning. As for expert decoupling, we oversample real datasets into a balanced version, then train a representation expert on real set and fine-tune it on balanced set to get classifier expert. We use classifier expert to initialize the soft labels of the synthetic data. The student model is trained on the synthetic set and matched with both experts, as shown in the loss formulation here. We compare our methods with the state-of-the-art approaches under varying imbalance factors. We conduct experiments on CIFAR 10 long-tail, CIFAR 100 long-tail, tiny ImageNet long-tail, and ImageNet 1K long-tail. Our method consistently outperforms existing ones across all settings, and the performance gap widens as the dataset becomes more imbalanced. We also conduct cross-architecture evaluations to verify the generalizability. Finally, here is a visual comparison. For head classes, both our method and baseline perform well. But for tail classes, as the imbalance increases, the baseline produces more distorted images, while our remains stable. Thank you.